Okay, so this is the third and final podcast for the atoms unit, and this is about isotopes. Alright, so let's go ahead and take an atom. We have two atoms, atom A and atom B. They have the same number of protons, different number of neutrons. So let's go ahead and make them and try to draw those. Okay, so we've got, let's say that's a proton, that's a proton, that's a proton, and that's a proton, that's a proton, whoops, that's a proton. Let's pretend they're the same size. And let's change the color for the neutron. So this one has 1, 2, 3 neutrons, and this has 4 neutrons. 1, 2, 3, 4 neutrons. And the neutrons and protons would both be in the nucleus. And then we have, each has 3 electrons. So let's take the, let's make this a little bit different. Let's make them black. And let's say there's 1 here, 1 here, oops, 1 here, and 1 here. They should be a whole lot smaller than the protons and neutrons, right? Because they're like 1/2000th the mass. They're tiny, tiny in comparison. Certainly not drawing them to scale. Okay, so what we have a new, cleaner picture of those two atoms, atoms A and B. And so the first question is, which element is atom A? And in order to answer that question, I had to look at the periodic table, because if you remember, the number of protons is what defines the element, because that is the number of also the atomic number. So if you only see one number on a periodic table, that's the atomic number, and it's got 3, so it's got 3 protons, which defines it, so it is going to be lithium. Because atom B also has 3 protons, that will also be lithium. So the main difference between A and B then is, the only difference is there are 3 neutrons for A and there are 4 neutrons for B. So that would be the number of neutrons. Okay, so next question is, which atom is more massive? So if you remember, we only counted, when we look at the mass of the atom, we only counted what was in the nucleus, because the electron mass was insignificant in comparison. So if we count the number of protons, 3, plus neutrons, 3, we get a total mass number of 6. If we do the same thing for atom B, we get 3 protons, 4 neutrons. That mass number is going to be 7. So the mass which is more massive is going to be atom B, and we wrote the mass number for each. So it also says write the isotopic symbol for each. Now this is the first time we've used that term, and what an isotope is if I have 2 variations of the same element. If this atom has lithium, these are both lithiums, right? We said this is lithium and this is lithium. The difference is that they have different number of neutrons, and therefore different mass. So the symbol I can write 2 ways. I can write lithium, and down here I would put the atomic number, and up here I'd put the mass number. So that'd be the atomic number at the bottom, and that would be the mass number at the top, right? And this would be then lithium also. It's always going to be 3 for lithium, and then it would be 7, because that's the mass number with the 4 protons. The other way I can write this, and probably more commonly written, is lithium 6. The 3 is assumed because it's lithium. All I need to show is the mass number. So this would be lithium-7. Okay, so the second question is, if I had an equal mixture of atoms A and B, what would the average mass be for the mixture? So if this has a mass of 6 and this has a mass of 7, then the average, if there's an equal number of both, would be right in between. It would be 6.5. Now, if you had a mixture of both atoms A and B, and the average mass was 6.94, which atom is more prevalent? Well, that answer would be, because the 6.94 is much closer to 7, I must have a lot more of these 7. So I'm going to have atom B. So let's just take a few notes. You can pause this as you need to write these down. So an isotope is an atom of an element with different number of neutrons, and because it's a different number of neutrons, and neutrons contribute to mass, they therefore have a different mass. For any given element, any naturally occurring sample I get of that element, it doesn't matter whether I get it out of a cave in Ecuador or I get it out of a mountain in Colorado, the element is going to have the same percentage of the different isotopes, and we call that the relative or the percent abundance. So for instance, if I take a sample of hydrogen, there are 3 isotopes of hydrogen, and the one that is by far the most prevalent is the one we know that has 1 proton, no neutrons. So that's got an isotope of 1, and you can see 99.985% of that atom or that element is hydrogen 1. A very small amount, 0.015%, is H2, and H3 is a negligible amount. This is the only isotope, hydrogen has the only isotopes that have actually been named, and you've probably heard these names. H2 is called deuterium. I'm not sure if it's DEU or DUE. Deuterium, I think it's DEU, and then H3 is tritium. And where you probably heard about these is the work for producing the atomic bomb, the hydrogen bomb, which required either deuterium or tritium. Very negligible in terms of how much there was, so it took a lot to get those. When you hear about uranium enrichment, as it turns out, there are many isotopes of uranium. Uranium is U, and there's only one of them, I believe it's uranium-289, that is fissionable. So this is the one that would be used in nuclear reactors to make nuclear power. But as it turns out, only a very small percentage of it is naturally occurring in any uranium sample. So in order to get enough to make a fission reaction, you have to have a whole lot of uranium-289, which means you've got to enrich your sample to get a higher percentage of this. Okay. So the number on the periodic table, as it turns out, is an average or a weighted average atomic mass, and often just called atomic mass. So in order to talk about how to calculate that average, I thought it would be helpful to use an analogy first. So let's say I had 100 students and their test scores were as follows. 15 of those students got 100, 50, half of them got an 80, 35 got a 60. Now, these are kind of evenly spread around 80, but the average, I could take these 3 numbers and average them, and it would come out to be 80. But what I see is there are a smaller percentage, 15 out of the 80, or out of the 100, that gets a high score of 100, and a higher percentage to get the low score of 60. So if I actually take a weighted average, and I take 0.15, because it's 15% of the students times 100, plus 0.50 times 80, plus 0.35, because it's 35%, times 60, and then add up those values, I get 76. Okay, so you calculate the average atomic mass in exactly the same way. So let's take a look. Here we have an example for chlorine, and we have chlorine-35 accounts for 75%, predominant isotope of the naturally occurring chlorine atoms, and chlorine-37 is 25%. So what is the average atomic mass? So I take the 35, this tells me it weighs 35. It weighs 35. I'm going to take that times 0.75 because it's 75%, and I get that. I'm going to take 37, which is the mass of the other isotope, multiply it times 0.25 because that's its abundance. Get that. I add them together, and this is what I get. Now I'm putting this unit here, AMU, which means atomic mass unit, and we're going to talk about that a little bit more. Okay, so let's compare this number. If I look at that 35.50 AMU, it is very similar to what I see on the periodic table for chlorine. If I had used more sig figs in these masses or these percentages, I would have come out with 35.45. So this number on the periodic table is the weighted average of all the isotopes. So let's write that down. It's the weighted average of all isotopes. And they're weighted based on their percent abundance or their natural abundance. Okay, that's what this number is. And it's often just called atomic mass. So if you see two numbers on the periodic table, the smaller of the two is the atomic number. The larger of the two is going to be the atomic mass. Okay, so now we're going to talk about how do we go from this unit of mass when we're talking about an atom to grams. Grams, something we can actually measure. Okay, so on the periodic table, the larger of the two numbers is going to be the atomic mass, and it's going to be listed in what's called AMU, or atomic mass units. But what's really convenient is that number on the periodic table. In the case of chlorine, it was 35.45. Also is the mass of a mole of those atoms in grams. Okay? A little bit confusing. So what is a mole? So a mole is a counting number, just like a dozen. A dozen is a counting number. That means 12. Or a gross is a counting number, and that means you got 144 of something. If I have a ream of paper, that means I have 500. So these are counting numbers that make it easier to talk about quantities. And it's actually defined as the number of atoms in 12 grams of carbon-12. Okay, so it was defined this way so that AMU and grams would have the same number, just different units. And as it turns out, while these numbers are nice and easy to comprehend, this is an absolutely enormous number, this counting number. And that's because atoms are so tiny that in order to get a weighable amount, you need a whole bunch of atoms. 6.02 times 10 to the 23rd. That's a number you're going to have to know. It's called Avogadro's number because, of course, Avogadro is the guy that came up with the number. Often confused with avocado. It's not an avocado, but it's Avogadro's number. And this is what it is, 6.02 times 10 to the 23rd atoms. So let's take an example. Here we have cesium. That is 75% cesium-133, 20% cesium-132, and 5% cesium-134. Alright, so we're going to do just what we did. We're going to take the 0.75 times the 133 mass, the 0.20 for the 20% times the 132 mass, and the same thing with the 134 mass. Multiply them and add them together. So I get 132.85. So what that says then is I have one cesium atom weighs that many AMUs, but a mole of those atoms weighs 132.85 grams. Okay? So if I have that Avogadro's number, 6.02 times 10 to the 23rd, which is called a mole, just like 12 is called a dozen of atoms, I have that many grams. Okay? Now we can compare cesium's atomic mass, what we just calculated, 132.85, and it's pretty close to what's here on the periodic table. And again, if we had sig figs, more sig figs on these, it would have come out to be exactly the same. So that's going to do it for isotopes.